This is video 3 in our Analytical Mechanics series. A reminder that the playlist for all the videos is featured at the website digital-university.org. What we're going to do is just spend a few moments examining the Euler equation that we had derived in video number 2. What we said is that we considered a general function f, and it was a function of x, y, y prime, and x is the independent variable, and being integrated from x1 to x2. And we want to find the stationary functions of this integral, and in doing that we derived the Euler equation, and it came out to be this form. Okay, x is the independent variable, so we're taking d dx of the partial of f, and it's always with respect to the one that we're going to take it respect to is the one that is the derivative of something, y prime. Then it's minus the partial of f with respect to the dependent variable, and that's y. Equals 0. So let's just consider some other general forms of the Euler equation and just kind of see if we can follow this pattern. So for example, suppose we had this integral in general form. I'm not going to bother putting the limits on it. Say it's f of, have it in polar coordinates, r, theta, theta prime, dr. So r is the independent variable now. Theta prime, of course, means the derivative of theta with respect to r. So if this was the general form, what would be the corresponding Euler equation? So we have d, r is the independent variable, so it'd be d dr. Then we would have the partial of f with respect to theta prime minus the partial of f, and the dependent variable is theta, equals 0. So we're just trying to follow the pattern from the very first Euler equation that we derived. Let's say that we have the integral, and the function is this general form, f of t, where t is time, x, and x dot. Usually you see us do this in the other videos too. Here, if we're taking the derivative of theta with respect to r, we'll say theta dash. If we're taking the derivative of some variable with respect to time, instead of dash, we'll use a dot. And this is now, time is the independent variable. So here, if the function was of this general form, the corresponding Euler equation, t is the independent variable, so we'd have d dt of the partial of f with respect to, let's get this in better focus, t is the independent variable, so it's d dt, the partial of f with respect to x dot minus the partial of f, and here the dependent variable is x equals 0. So a function of this general form would have this corresponding Euler equation. Now, notice that for each one of these examples, we had one independent variable and one dependent variable. Independent variable and a dependent variable, and independent variable and a dependent variable. What happens if we have a function that might have several dependent variables? So let's just say that we have a function of this general form. Say it's like this, integral, and we have f, and say we have x, y, z, then we have y prime, say z prime, dx. So x is the independent variable. And then we would ask for a function of this general form where x is the independent variable, but now we have two dependent variables here. What would be the corresponding Euler equation? And we would have an Euler equation. We're not going to prove this, but we're just going to sort of follow the general pattern. The corresponding Euler equation we would have one for y and y prime, and z prime. So again, x is the independent variable, so it always starts off with d dx, and then we would have the partial of f, say with respect to y prime, minus the partial of f with respect to y. Y is one of the dependent variables. We use the one that corresponds to the y prime, equals 0. That would be one Euler equation. Then the other one, x is still the independent variable, so it's still going to be d dx. Only here we'll have the partial of f with respect to z prime minus the partial of f with respect to z equals 0. So here we had we had one independent variable, two dependent variables, so we have two corresponding Euler equations that came out of this. Now, suppose that our function was like this. We did not have z. We have z prime, we have dz dx, but not z. Then, of course, this would be missing. So in that case, the corresponding Euler's equations would look like that. Okay, that's all we're going to do in this video. We just want to take a few moments and kind of familiarize ourselves with what the Euler equation might look like in different circumstances. And again, we didn't really see a lot of insight to it. All we did was just try to follow the general pattern. But hopefully that will help set the stage for the next video when we consider Lagrange's equations. So come back and join us for that video, and then we'll start to get into more specific problems.